Wireshark can be used to capture data. You can also use it to analyze existing data that you've captured. A bunch of different tools can capture network traffic. When it's captured in a standard format, it doesn't really matter what program you use to capture that data. A lot of different tools can be used to analyze it. So this time we are going to take a look at Wireshark, and we're going to use Wireshark to analyze existing data that's been captured. So I'm going to scroll down again to the hands-on portion. There's a few files that I've already created that capture different protocols, different network traffic. So I'm going to go ahead and download these files. So there's ARP, the address resolution protocol. I'm just going to save all these to my desktop just for now, just to make it easy to see where I'm putting them. Just going to download all of these packet capture files. And we'll open them up one by one. I'll just have them all ready to go. All right, so they're there on my desktop. You can see those files just showed up. I've got Wireshark installed, so all I have to do is double click on one of these. They're registered in Wireshark. So let's take a look at ARP. I like this protocol. Why do I like this protocol? Well, it's fairly simple. So I've only got 2 packets in this capture. It's a fairly straightforward capture. We've got 1 packet, the first one. So we can, packet number 1, we got packet number 2. We can see the time here didn't take long to get a response. So my computer was the source, and I sent out a broadcast message. So everybody on my local network got this packet. So we see the protocol is ARP, the address resolution protocol. And let's just take a look at this. It says in the info, who has 192.168.140.2, tell 192.168.140.131. So my computer needs to send a message to the computer 192.168.140.2. I know their IP address, but I don't know that computer's MAC address, their physical address. So the address resolution protocol is linking those two things together. Now, everybody on my local area network gets this broadcast message, but everybody ignores it except for the one computer who has that IP address. So I got a response from that computer that had that 192.168.140.2 IP address, and it responds to me and tells me, hey, just so you know, 192.168.140.2 is at, here's the MAC address, that hardware or physical address of that computer. So once my computer has resolved this address, and I have their MAC address, then my computer can send a message directly to that computer using its MAC address. So we can see, if I make these a little bit bigger, I'm zoomed in. So originally the source was my computer. That's the hardware address of my computer. The destination was a broadcast going to everybody, but the reply came from that one computer who had that IP address. And the destination in this case was just a single recipient, my computer here. So we see the 64BE6F was the source originally. The second packet that I captured, the destination was that 64BE6F computer. So I like this protocol partially because it kind of reads a little bit like English with a little bit of networking sprinkled in there. We just look at that info column and it kind of tells us what's happening. We can see that communication happening. So that's the address resolution protocol. So I'm just going to close Wireshark. We're just exploring the interface. Let's take a look at ping next. So if I ping another computer, I'm testing connectivity. So let's take a look at this packet capture. Who was I trying to ping? Well, we can see this first packet, what kind of protocol is being used. It's DNS. This is a standard query for the A record and the AAAA records in packet number 2. That's the IP version 4 address and the IP version 6 address. So I issue those queries and then I get a response. So I tried to ping google.com, but I need to know Google's IP address. So the first thing my computer did was issue a DNS request. So I see those requests and then I see the responses. Now, once my computer has resolved the IP address, then it's actually going to send the ping request. So my computer is the 140.131, and Google's going to be this 172.217.2.46. That should match what DNS gave me. DNS told me that Google server was at 172.217.2.46. So yeah, these addresses match. So part of what I'm doing is just matching up the requests and responses and seeing how this worked. So I see the request, and then I got back a reply. Came fairly quickly. I can see a couple of requests and replies, which is totally normal because typically your computer won't just ping one time, it's going to ping a couple of times. On Windows, it defaults to 4 times. It's going to send out 4 requests and look for 4 responses. On Linux, the ping utility will ping multiple times until you cancel it by default. So I might see 4. So I see 1 set, 2 sets, 3, 4, 5. Ping requests and replies. And so this is good. We're just seeing the combination of the name resolution with DNS. We see the request and then the reply. So take a look at the source and destination here. Obviously for the request, I'm initiating it. So the source is going to be my computer. The destination is Google. When Google sends that reply back, the destination is going to be my computer. And the source in this case is going to be Google. So we can see some data about the request. Everything looks good here. Let's take a look at some clear text network traffic next. So I've got clear text website.pcapng. So again, you can see what website I was visiting just looking at this network traffic. You didn't have to be looking over my shoulder to see my web browser. I can see the DNS query. I was trying to go to neverssl.com. I got its IP address, and I could then go out to visit the website. So if I scroll over, I'm zoomed in a little bit just to try to make it more readable here, but I see, yeah, the IP address is 34.223.124.45. Then I see I actually create a connection to that IP address to transfer the web page. So if I find this HTTP packet here, I can right-click on this packet, packet number 11, and I can follow HTTP stream. So one web page might be broken into a bunch of different chunks, and that might be sent to you in several different network packets. Following the HTTP stream is going to find all of those individual packets and shove them all together, and we can take a look at what this website was sending. Now, it's not a beautifully rendered website like you might see in your web browser. We're looking at the raw HTML, the hypertext markup language. This is what your web browser would render and show you on the web page. We can, once we've followed one HTTP stream, if there are multiple, it says I've got 3 total streams. So I can use these arrows here to navigate between them. Some are more useful than others. Looks like I wanted the icon there. Looks like it came through as an image. Yeah, that image it's not going to show up well in text here. But we can take a look at all of this data. So because it's unencrypted, anybody who could capture this network traffic is going to be able to read this data. One good reason for encryption. So following the streams can be really helpful for reassembling all of these packets into something meaningful. Otherwise, these little bits and pieces of data can be hard to combine into one meaningful object, let's say. I'm going to close that. I'm going to pull up, let's take a look at the encrypted web traffic. So go into Wikipedia. Wikipedia, by default, if you try to go to Wikipedia, it's going to send you to the encrypted version of Wikipedia. So we can see first, I did a DNS request for Wikipedia. DNS told me where to find it. So I see an IP address there, so that's good. Then I established a connection here, but I don't see the HTTP protocol. Instead, I see TCP packets, and I see this TLS version 1.3. So TLS, that's Transport Layer Security. That's essentially the S in HTTPS. This Transport Layer Security is going to send all the data in an encrypted format. And I've got a whole bunch of packets here. So if I follow those packets, if I try to reassemble them, if I right click on one of these TCP packets and I follow TCP stream, here's what I get. Hard to read because this data is encrypted. So I can't see the contents of what Wikipedia page I was really looking for. Was this a home page? Was this an article on cybersecurity? Who knows, right? It's just a bunch of scrambled data. So from a privacy perspective, this is good. That means people eavesdropping and sniffing our packets out of the air, they're not going to be able to read this data. Also, if we had a malicious internet service provider or some rogue device that happened to be capturing these packets, they can't inject ads. They're not going to steal our usernames and passwords, all that kind of stuff. So this is good. I can go through these streams and try to see if there's anything useful. Not really. Got to the end there, and it's all encrypted. So that's a good thing for us. So the clear text web traffic and the encrypted web traffic, both of those files were generated using a web browser. The only difference is that one of them used HTTPS instead of HTTP. I'm going to close that down and scroll down. Computer slowing down just a little bit. I'm going to take a look at a port scan next. So port scans are used by information technology administrators to verify that their security settings are in place. Port scans might also be used by hackers to try to look for weaknesses in a target's environment. So what's happening here? Well, there's a lot happening here. One thing to pay attention to is the destination port. One sign that a port scan might be happening is that there's a lot of packets going to a lot of different ports. Basically, what my computer was doing in this port scan, like here's my computer and there's the destination that I was doing a port scan on. I had permission to do this port scan, so wasn't doing anything crazy. But for example, port 25 is used by the Simple Mail Transfer Protocol. My computer was saying, hey, remote computer, are you running email? Trying to see if it's open. So it's going out to all these ports and trying to figure out, is something running there? And so if you're not familiar with the ports, this isn't going to make a whole ton of sense. It's just going to look like a bunch of random noise. Port 53 is used for the domain name system for DNS lookups. So I might want to know, is this server running a DNS server? So my computer is going out and it's trying to collect this information. So if I'm a network administrator and I'm looking at this kind of traffic, I might wonder, like, what the heck is this person doing on my network, trying to scan all of my ports and to see what I'm doing? Maybe I don't want that person doing that. Maybe I'm going to call them up on the phone and be like, hey, Chuck in accounting, why are you running a port scan on my server? Looking for anything in particular? This kind of port scan can raise alarms automatically. It can be detected, and this could be flagged. We could say, all right, looks like Chuck's running a port scan. Maybe we should stop Chuck from doing that right now, because Chuck in accounting shouldn't be running port scans. Maybe Chuck's got some malware on his machine that kicked off a port scan in the background, so maybe Chuck doesn't even know. So these kind of traffic patterns are something that, as you get more used to analyzing network traffic, you can take a look at a file like this and you can kind of reconstruct, okay, I can kind of see what's going on. It's kind of like Neo from the Matrix, looking at all those kanji characters, trying to make sense of the Matrix. That's kind of what it might seem like at first. It's just a big wall of data, but the more familiar you are with network traffic, the more sense these kind of files are going to make. I know some people who have applied for jobs in cybersecurity. As kind of a pretest, and a potential employer will send the candidate some of these capture files and just ask, like, hey, can you give us a summary of what was happening on this computer based off of the network traffic that you see in here? Sometimes you can identify attacks. Sometimes it's just somebody browsing a website, doing nothing nefarious at all. But this is the raw stuff happening on the network. The automated scans, some of the really big platforms that cybersecurity companies sell clients to protect their networks, they'll be scanning those kind of packets constantly, looking for signatures of attack. So take some time looking at those files, try to make sense of them, click around, poke around. You're not going to hurt anything in Wireshark analyzing those packet captures, but analyzing this data is something that cybersecurity professionals do. It's what the tools do in the background to protect our networks. It's one of the layers of security that we have in place to make sure that the network traffic happening on our network is what we want to happen. And if there's something that we don't want to happen, we might need to take some proactive action.